Okay, we are on to the second question of the few response questions I gave you guys. So we've got an astronaut holds a rock 100 meters above planet of X. So we don't know the acceleration because we're on a different planet. The rock is then thrown upwards at a speed of 15 meters per second, and the rock reaches the ground 10 seconds later. And we're ignoring air resistance when it is in free fall. Okay, so we want to know, what is the acceleration of gravity on planet X? Okay, so what are some things that they told us? We know the initial velocity is 15. We know that the displacement is right here. And we know the time, because they told us, takes 10 seconds. Okay, so it looks like we can use this equation. The displacement is equal to initial velocity times time plus 1/2 the acceleration times time squared. Okay, now you got to be careful because you can make a mistake here. The displacement is not 100. The reason that is here's where he starts, right? So here's 0. Here's what it ends. Displacement is change in position, which means the final position minus the initial position. Okay. So the initial position is 0. And the final position here, if this is 0, this has to be negative 100. Okay. So our displacement is actually negative 100. Our change in position is negative 100. Okay. The initial velocity was 15. And we did that for 10 seconds. Or the change in time is 10 seconds. Plus 1/2, we're looking for acceleration. Time squared is 10 squared, so that's 100. That means this is negative 100 equals, this is 15 times, 15 times 10 is 150. Plus half of 100 is 50A. Okay. Move this over to that side, that's negative 250 equals 50A. Which means that if we divide both sides by 50, we get negative 5A. And units for acceleration are meters per second every second, meters per second squared. The reason it's negative is the acceleration is downward. So how does the speed of the rock when it reaches the ground, compare with the speed of the rock thrown upward? Okay, so the rock's going to go up and then come back down like this. Okay, now when we throw the rock up, what is the speed here? The velocity here is 0. Okay, so it's going to slow down till it hits 0. It's going to come back down. It's going to speed back up. When it reaches this point here, the same point there, what is the speed? The speed, or the velocity, is now negative 15. At the same height, the magnitude of the velocity is in the same, just different direction. Okay, that means it's sped up from 0 to 15 here. That means it's going to speed up even more by the time it reaches the ground here. Okay, so the velocity at the ground is going to be greater than the velocity when it was thrown upward. Okay. Another way you can think of it is, at this point, when we throw it here, it's got kinetic energy, right? That kinetic energy is converted to potential energy, which will all be converted back to kinetic energy here, the same amount of kinetic energy at these two spots. Okay, so that's why the speeds here should be the same. And then here it's going to more kinetic energy as the potential energy is decreasing. Perfect. Student wants to know how the motion of the rock would be different if it was thrown. So we're still throwing at the same speed, at the same height, but now we're at Earth's surface. Okay, so planet X's acceleration was 5, and Earth's acceleration is 10. Okay. In a clear, coherent, paragraph-length response that may also contain figures and/or equations, explain how the motion of the rock would be different in terms of its maximum height above the ground, the speed at which it hits the ground, and the time at which it's in free fall. Okay, so we need to talk about three things it's saying here. The maximum height above the ground, the speed at which it reaches the ground, and the time at which it is free fall due to acceleration of gravity. Okay, the first thing you need to say is that Earth is 2 times the acceleration of planet X. Okay, I can't, it's very hard for me to write it out with a mouse, but Earth's is 2 times the acceleration of planet X. Okay, so it's more acceleration on Earth than on planet X. Okay, so since the acceleration is greater on Earth, the time, so we want to know the time it takes. So here's the rock and here's the cliff. It's going to go up and then back down. I want to know the time it takes to get to this point here. Okay, meaning the time it takes to stop. Okay, how long would it take to stop on planet X? Well, what does acceleration mean? It means that how much the velocity is changing every second, right? So if I threw it upward at 15, after 1 second, it would, remember these are negative. After 1 second, it would slow down by 5. So after 1 second, instead of being 15, it's now 10. After 2 seconds, when it's slow, it'll be at 5, and then after 3 seconds, it'll be at 0, okay? Remember the velocity at the top here is 0. So on planet X, it would actually take 3 seconds to slow down, okay? At on planet Earth, you would take 1.5 seconds to slow down. So it's actually traveling longer on planet Earth, which means it's going to go a further distance, right? The time it takes for the rock to reach its maximum height is less on Earth than on planet X. Okay? So time is less on Earth to reach max height. And since it's traveling for less time, right? Less time, that means less distance. Okay? This also means the time in which it is in free fall. Okay? We just said that there's greater acceleration here, so the time it is in free fall will be less on Earth. Time less on Earth, free fall will be less. This is Earth. Okay? Now we got to talk about this. The speed at which it reaches the ground. Okay? The speed at which it hits the ground. So let's look at an equation. Let's look at this one. The final velocity squared equals the initial velocity squared plus 2ax. Okay? So what this shows is that the initial velocity stays the same, right? So we'll plug in a 1 there, right? This 2 is going to stay the same, so we'll put a 1 in there. This displacement is going to stay the same, so put a 1 in there. However, we doubled this, right? So the final velocity will actually be the square root of 2. Okay, which I think is about like 1.4. Yeah, it's 1.4. So it will hit the ground with 1.4 times the speed as on planet X.